Closely related to P&ID diagrams are loop diagrams. Now, P&ID diagrams will vary quite a bit in their layout. There's a lot of freedom for the designer, whereas loop diagrams are much more standardized. And so generally, well, in loop diagrams, you go from the process, the field side on the left, to the control room on the right. So the panel front, essentially, on the right. Now, there can be a field panel along the way. In other words, there can be something out by the process somewhere where maybe there's an indication of the current temperature or whatever the case may be. In this case, there's a pressure difference. So we're going back and looking at that compressor from earlier. But this is more detail. So we're zooming in farther than even the P&ID. So this includes the details of how things are wired together. So there's even all the way down to wire colors and terminal numbers so that you can more easily troubleshoot a system or build the system or whatever the case may be. Now let's look at this and understand it. Let's start off, we'll go through each row and try to understand it. FE42, well, what's that? Well, it's on the left at the bottom, flow element 42, and so this is a flow nozzle. It necks down and changes the pressure so that we can infer the flow rate. It's a venturi tube. According to this, I thought it was a flow nozzle. That's what that symbol is a flow nozzle, but they're claiming it's a venturi tube, so okay, fine. But that's not the standard symbol for a venturi tube, but okay. And notice that all of these instruments can be looked at as input and output. So there's some type of input relationship and then an output. So for example, the input for this flow element would be a flow rate. Maybe 0 to 1,500 standard cubic feet per minute, and that's what it's shown in this case. And what it outputs is inches of water column. That's what that double quote WC stands for. Really, it's a measure of pressure. And it would be a pressure difference that should be measured here, but that would indicate then the flow rate. So at 0 SCFM, we should get 0 inches of water column. This is referring to a manometer. And then at 1,500 standard cubic feet per minute, we should get 100 inches of water column out of this flow element number 42. Now, FT42 is a flow transmitter, and when it measures 0 inches of water column, it will output a 4 milliamp current signal back to the controller. And when it measures 100 inches of water column, then it's at the high end of the range, 20 milliamps. Now let's trace FT42 all the way through to the flow indicating controller. You notice there's a plus minus. So red wire goes to the plus terminal, a minus goes to the black terminal. It's indicated it's supposed to be a 4 to 20 milliamp signal, and these two wires are carried in cable number 23. They go to a field panel where they connect up to terminals number 14 and 15, and then terminal 16 indicates a shield, some type of grounded shield most likely, for the sake of avoiding interference in the wires. Because understand, although these look short on this diagram, the wires going from the field panel to the panel rear in the control room are probably quite long, and that's one of the reasons for using a current signal. So there's a lot of space between terminal 14 and terminal 7, terminal 15 and terminal 8, between the field panel and the panel rear in the control room. But if we continue going along from terminal 7, 8 at the panel rear, then you'll notice that that goes into a plus-minus terminal into FY42A, which happens to be the next item in our table. Now, what is FY42A? Well, it's a square root extractor. So F means a flow rate. Y indicates a relay. What they really mean is not a relay, but a function, a mathematical function. And it's taking the square root of the 4 to 20 milliamp signal. Why? Well, if you know anything about fluid flow, you know that when you cause a pressure drop in a pipe, that pressure, or the flow rate, will be proportional to the square root of the pressure drop. That's just a principle from flowing fluids, from fluid mechanics, really. And so the 4 to 20 milliamp signal is not really linear with flow. It's nonlinear with flow, but the square root of it will be linearly related to flow. And so the plus-minus terminals on the right-hand side of FY42A continue on with a 4 to 20 milliamp signal to terminals number 5 and 6 on the flow indicating controller number 42 on the panel front. But you'll notice that underneath FY42A there's a little box with a square root sign in it, indicating that FY's job is to take the square root of the incoming signal and output that. So you'll notice that on FY42A, the row down in the table, it says the input is a 4 to 20 milliamp signal, but the output's a 4 to 20 milliamp. And of course, the difference between those two is those two 4 to 20 milliamp signals are not linear related. One is the square root of the other, or is proportional to the square root of the other. And the purpose of that is so that we end up with a signal that really indicates something that's flow rate and not just pressure drop for the sake of flow indicating controller 42. Now what about FY42B? Well, that's connected, if we go all the way back to the field process area, that is connected to a valve, and that valve is made to close open, you notice? Which makes sense. Remember, the purpose of this valve was to unload the compressor. And if the valve were to fail, we'd like for it to fail open so the compressor is not damaged. So FV42, of course, is an anti-surge control valve, skipping down one row in the table. It accepts a 3 to 15 psi signal, and it outputs a 0 to 100%, closed to open or open to close. Let's see, 3 would be, yes, so it would fail open, so 100% open. So it requires air to close. There's a note there on the right that indicates that. So this would fail open. Now, FY42B that's connected to the valve, to that flow control valve, notice they've labeled it FV42, but I would call it an FCV, not just an FV. That FY42B, going back up one row, what it does is it converts a current to a pressure signal. Now notice that there is an arrow just below the box that's labeled I to P next to FY42B. That arrow points upward. What it indicates is that there is a direct relationship between FY42B's input and its output. In other words, when its input increases, when the current signal coming into it goes up, the pressure signal coming out of it goes up. It increases the amount that FV42 is closed. So it's a direct relationship because an increase in the input increases the output. And so that, of course, FY is something that the controller manages, it controls, and that goes back through terminals 11 and 12 in the field panel, connects to the panel rear at terminals 4 5. It's cable number 26, another red and black wire that go to terminals 3 and 4 on the flow indicating controller. Now the last bit to think about is the pressure differential transducer, PDT, and that's on the upper left, but let's trace it from the flow indicating controller. So it's terminals 1, 2 on the flow indicating controller. That's where the signal comes into that controller. Connects to terminals 1 and 2 on the panel rear, and then terminals 8 and 9 out in the field panel, through cable 21 to red and black wires that are 4 to 20 milliamp signal from the pressure differential transducer. Now remember, what this thing's supposed to do is measure the pressure difference across the compressor in order for the flow indicating controller to react by opening or closing the valve. The pressure difference across the compressor becomes too large. Now you'll notice that on PDT42, of course, we've got our wires come in on the right. We've got H and L. I think that probably H and L indicate high and low, and I suspect they're backwards here because the high side of the compressor is coming out the top. That's where this pressure is going to be high. And maybe there's something I don't know about loop diagrams and this is correct, but I would have switched the H and the L based on what I think I know. But the PDT42, that pressure differential transducer, that's our element that's measuring and transmitting the signal to the flow indicating controller. And of course it measures a 0 to 200 psi signal, so that's the maximum pressure, I guess, that we want to measure across this compressor. But notice it outputs a 20 to 4 milliamp signal. And of course this is indicated by the arrow to the left of the box, the 0 to 200 psid up by the PDT42, indicating this is a reverse action. So an increase in input decreases the output. So there's reverse action. There's even notes in that next to last row in the table that this is a reverse acting thing. So as the pressure difference across the compressor goes up, the millivolt signal coming out of this PDT goes down. And of course the reason for this is if the sensor were to fail somehow and we just got a low reading all the time, we would assume that it's high pressure across the compressor. That would be a safe failure mode. So FIC42 is of course the anti-surge controller itself, and it inputs 4 to 20 milliamps from actually two different sources, from flow transmitter 42 and from pressure differential transducer 42, and it outputs a 4 to 20 milliamp signal to FY42B in order to control the surge valve. So this is nice because there's a lot of detail. There's even information about how these various things are powered. For example, you notice flow indicating controller 42 has terminals L1, L2, and G. So L1, L2 would be line, basically a hot and a neutral, and G would be ground. And then, of course, FY42A has some terminals above it, G, L2, L1, similar to what we have for the flow indicating controller, just 60 hertz, 120 volt AC standard current available, AC current, to operate that device. Functional diagrams are very different, whereas piping and instrumentation diagrams and even loop diagrams don't show you the control strategy. A functional diagram does. So it eliminates a lot of detail, but it shows you whether it's feed forward, feed back, what kind of controller is implemented, and so forth. So here's a very simple example where we have a flow transmitter. We're measuring a flow rate. We've got a PID controller that then looks at that flow rate, and looks at the error, the rate of change of the error, and the integral of the error over time, and changes the flow control valve in order to change the actual flow rate going through and sensed by the flow transmitter. It's a very simple feedback control system, and you can see what this does. It's labeled as a PID controller. The symbol makes that obvious. We can even indicate a cascade control, as you see here, where the level, say, in a tank is measured, and there's a primary controller on the left that is doing PID control and provides the set point for the flow PID controller on the right. And so this is a classic cascade setup, and it's easy to see that that's what it is. Now there's other information that can be included in functional diagrams. You notice these symbols ATA that have been added. What are those? Well, T is for transfer, and the 2A means a manual override where you can manually set things. The one on the left indicates that you can manually set the set point for the PID controller, whereas the one on the right indicates you can manually set the output of the PID controller. So some modifying symbols there. A deeper look into this, an expansion of the last image is shown here, where now notice that we've got this rectangular T up and to the left. What does that indicate? Well, it indicates that we can either feed in the set point to the PID controller from the measured signal or from another source, a manual source, and I'll explain that in a minute. But why would we want to make the set point on the PID controller equal to the flow rate that's being measured? Well, remember, the purpose of this PID controller is to control flow rate, right? Well, if the set point is equal to the process variable and error is always, the difference between the two, then there's always going to be zero error. In other words, the PID controller will not try to manipulate the output variable, right? The control variable will not be changed. In other words, the controller will be in manual mode. And so we can either choose to have the information, the analog signal of flow rate, go in as the set point for the PID controller, or it can come from another source. Now notice that dashed line at the bottom. That's actually a discrete signal. In the world of functional diagrams, solid lines indicate an analog signal or a continuous signal, whereas dashed lines indicate an on-off thing. So the idea here is that either the set point is controlled by a set point that the user inputs, that's the A on the left of that box T, or it's controlled by the user setting it, and that's what the dash line is at the bottom. And so since that's a selection, that's an on-off type of thing. This is how it's indicated in a functional diagram. There are many standard functional diagram symbols, and I'll let you look through these. These are primarily there for your reference. I don't intend to go through these in any detail. Notice PID controllers has two different standard symbols. Either one's fine. But we're not going to use functional diagrams much at all, if any, in the class. So we covered our process flow diagrams, piping and instrumentation diagrams, loop diagrams, and functional diagrams.